This lesson is the introductory lesson to ray optics. What we're going to be looking at primarily in this lesson is how to draw ray diagrams for mirrors. Before that, we're going to talk a little bit about light rays and go through a whole bunch of definitions, and then we'll do the ray diagrams. Okay. First off, we have to understand how vision works and how we see something, okay? We understand that light is an electromagnetic wave, but it generally travels in packets called photons, and these packets travel in a straight line until they hit a surface. Okay, and so when those photons hit the retina in the back of your eye, the rods and cones in your eye convert that light energy into neural signals, and these neural signals are then interpreted by the brain into what we think we see. Okay, so because the light rays travel in a straight line, a common model that we're going to do is to simply draw an arrow for the stream of photons leaving an object. For example, in the picture of this pencil, okay, photons are leaving this pencil in multiple directions. Actually, the photons are bouncing off the pencil since the pencil doesn't generate light on its own. Okay, it's only reflecting the light from the environment. Okay, but those photons are going to eventually work their way, and some of them will hit our eye, and we will then process that and say, oh, look, there's a pencil. Okay, but what happens when it hits a mirror, or what happens when it goes through a lens? Okay, before we do the ray diagrams, I have several definitions that we're going to go through. Okay, these definitions are also on your worksheet, but it may help to pause the video here and just go over all of these definitions. Okay, we're going to be talking about the object distance and the image distance, how far the object or the image is from the lens. The farther the object is, the larger the object will appear. Okay, an upright and inverted image, those are opposite terms. And then we also have virtual image and real image. Okay, we're going to go into these two words in a little bit more detail in the set of slides going forward. But understand that they are opposite terms, representing where on which side of the mirror or lens does the image appear. Okay. And then the last two are basically also opposites. An image will either appear larger or smaller, or in some cases exactly the same size. Okay, so the image size compared to the object size. Okay. Two final definitions, converging. An optical device, for instance, a mirror or a lens that focuses light rays as opposed to spread light rays out. That's a converging lens or a converging mirror. In this case, the mirror is concave and the lens would be convex. The opposite of that would be diverging, an optical device that spreads the light rays out. Okay, and in this case, the focal point is on the wrong side of the mirror. Okay, or in this case, it's a convex mirror or a concave lens. Okay. So first off, the most common mirror that we have is the plane mirror. This is what we have at our home for the most part. Okay, it's just a flat surface, and in this case, every time we look in the mirror, the image will appear to be upright and it will appear to be exactly the same size as the object. Okay, another way to describe this is that the distance of the object to the mirror equals the distance of the image to the mirror. Okay, so it's going to be upright, virtual, and the same size. Okay, concave mirrors, on the other hand, are designed to focus the incoming light from far away on a single point. That point is called the focal point, and we use the letter F to represent the distance from the mirror to the focal point. Okay, and it focuses the light based on the principle of the law of reflection. Okay, there's another point that we call the center of curvature. This is basically the center of the circle. If the mirror is a part of a circle, okay, the center of that circle is C. And it turns out that the focal point, if we go through the geometry, and I don't really want to at this point, the center of the circle and the focal point is going to be half of the distance, okay, halfway from the center to the mirror. Okay, so another way to say that is F is equal to C divided by 2 if we use C to represent the center of the circle. Okay. So besides a concave mirror, we also have a convex mirror, okay? This also has a focal point, but the focal point is the point where the the reflected rays appear to originate from. So it's on the other side of the mirror, and it's going to be a negative number. Okay, so the focal point for a convex mirror is going to be negative. So now we're up to ray diagrams. Okay, I'm going to go over 3 examples of ray diagrams. Okay, it's only going to be necessary to draw 2 of them. The third one can be used to double check your work. Okay, and the image, okay, these ray diagrams just give us a sense of where the image will be. Okay, and it's the image will be placed where the reflected rays intersect, not the rays originating from the object, but the reflected rays. Okay, so these are the 3 rays, okay, and pay attention to the order because the order is going to be important, especially when we get into lenses. Okay, the first ray that we draw is going to be parallel to the principal axis. The principal axis is that imaginary middle line that we have here. Okay, so we're going to draw the first line parallel to the principal axis, and when it hits the mirror, it reflects back through the focal point. Okay, so there's my first line. Okay, I draw it in blue because this is the original ray, not the reflected ray. Okay, the reflected ray is going to be in green, and it goes through that focal point. Okay, so that's the first one. Parallel focal is the way I describe it. Okay, the second one is similar, but it's focal parallel. Okay, so in this case, the originating ray is going to go through the focal point. When it hits the mirror, it's going to bounce back parallel to the principal axis. Okay, so there the green line is parallel to the principal axis. Where the reflected lines, okay, the green lines, where those intersect is where the image is going to be. So in this example, my image is clearly smaller, it's inverted, and because it's on the same side of the mirror as an observer, the observer would be on the left side. Okay, this is a real image. Okay. A third ray that we could draw, and in some cases it may be easier, but the third ray goes from the object through the center of curvature. Okay, and because my incoming angle and my reflected angle both have an angle of incidence of 0, there's no reflected ray. The reflected ray and the incident ray happen to be the same line. Okay, so that's the third ray, okay, directly through the center of curvature. Notice that all 3 rays intersect at the same point, okay, and that's the way we can double check. If we're just drawing it by hand, there's going to be a little bit of uncertainty associated with it, but it should more or less be in the same spot, okay, and so there again is my image. Okay. In the case of a convex mirror, the same rules apply, okay? But pay attention because my focal point and my center of curvature are on the opposite side, okay? But it's still going to be the same. I start parallel through the focal point, and then the second one through the focal point and parallel, okay? In some cases, I need to extend those reflected rays onto the other side of the mirror because they don't intersect on the left side or on the real side, okay? And you'll get some of that practice for homework, okay? Thank you.